Let's go ahead and get started. So, despite the technical difficulties, we are very happy to have Robin Cockett of the University of Calgary, who will tell us about Turing categories. So please, whenever you're ready.
Okay, so as I've indicated, this is dedicated to Pieter Hofstra, and nothing would have happened except for that he joined in on this. I'm not sure whether he joined in or he actually sort of initiated it. But okay, I hope you can read my scrawly writing. So the talk is based on, well, there's 3 papers. So this is not new stuff. It's old stuff. And the 3 papers, Introduction to Turing Categories, and that was done with Pieter. And it was the basic paper. And then an interesting paper, and I'm going to talk about it in some detail, was with Zemo Boyles, Jonathan Gallagher, and Pavel Hrubrez, right? And the Hrubrez is a complexity theorist, so it was very interesting working with him. And then there were some leftover issues which Pieter helped to solve on that, the total maps of the Turing category. And if you want to get into this, on my website, there are some notes. I call them the Estonia notes because I actually gave them as a series of talks in Estonia. So, so that should get you going. I don't have the exact references, but as you know, Google is wonderful. So, okay, so I met Pieter in Ottawa. I was on sabbatical and they gave me an office, and it turned out to be an office which I shared with Pieter. And of course, we got talking. And it turned out that Pieter had done his PhD using ordered PCAs, and computability was very sort of close to his heart as a result. And we got, well, so I was interested in it because I'd done this work on restriction categories. And the idea originally with the restriction categories was to look at computability, and I hadn't sorted out how to do it. But when we got talking, I realized that Pieter had the sort of answer to my problem. So I persuaded him to join me as a postdoc in Calgary, and he stayed for about 2 years before he returned to Ottawa as a faculty member. And we continued to work together. And of course, earlier this year, unfortunately, tragically, he died. And we developed the basic theory of Turing categories while he was a postdoc with me. Okay, so what are Turing categories? Well, the abstract computability. And so they have a notion of computable maps, and it's in a setting of partially defined functions. And that means that I've got to sort of talk about how you model partially defined functions. And obviously there's this relationship to partial combinatory algebras, because that's what Pieter was all about. Basically, one of the things we wanted to do was to reconstruct recursion theory, but categorically, using Turing objects and Turing maps. Okay, so here's the plan. We're going to start off by just reviewing restriction categories. So they're the abstract theory of partial maps. And then I'm going to talk about time sets and complexity for a while. So this is really a construction from CS, computer science. And then we're going to go back and introduce Turing categories. And the sort of particular example I'm going to sort of aim at for this talk. And then I'm going to talk about some open issues. Okay, so restriction categories I developed with Steve Lack. So just quickly, a restriction category is a category together with a restriction combinator, which given a map F from A to B, returns a map, it's an idempotent actually on the object A, on the domain of the map. And what this idempotent is supposed to represent is a partial identity, which defines where F is defined, right? This combinator just satisfies 4 identities. And I'm writing these in diagrammatic order as opposed to applicative order. So if you first do F bar and then you do F, well, that's the same as F. And you know, if you've got a partial identity, which just defines the domain of F, well, when you precompose F with it, it has no effect. So that's quite natural. And then, well, the second rule just says that when you take these partial identities, they commute. And that's quite a natural thing. And the third one says that you can take the first bar and you can sort of slip it under the second bar to get F bar G all barred, right? And that's the same as the intersection of the 2 restriction idempotents, which of course is the same as the composition. And then the fourth rule, which is the all-important rule, says that if you do a restriction after a map F, it's the same as first doing the restriction of F composed with H and then F. Okay, so that's the basic notion of restriction category, and we'll sort of come back to it. But I'm going to sort of interpose and say, okay, where did all this come from? So there's quite a long history of talking about partiality in various settings, and probably the oldest sort of coherent piece of work was by Carl Menger, and he was coming from calculus. So his idea was, if you were going to talk about calculus, well, you had to talk about partial maps because things weren't defined everywhere. And he had a series of students who actually developed this into semigroup theory. So the algebraic theory of semigroups with a restriction, although the axiomatizations were all a little bit different. And that, I mean, a particular example of that is an inverse semigroup. So coming from a different direction, Charles Ehresmann, of course, also looked at partiality from the perspective of differential geometry. And I sort of, Marco Grandis has actually just published a book on cohesive categories. And this, I mean, is equivalent to restriction categories. And I think he was sort of in the Ehresmann line of thought there. But also there was another sort of direction which took off, and that was from computability. And Paola and Hella tried to describe computability without mentioning elements. And in particular, they did have the axiomatization of partiality, but it was mixed in with all sorts of other axioms. So it was a little bit hard to extract what was happening. And almost immediately, Robinson and Rossellini sort of extracted the core of what they were doing into P categories. So these were things with partial products, and the axiomatization was around the partial product. And then actually quite 12 years later, at least, Steve Lack and I re-looked at it and realized you didn't need partial products. And that's where we introduced restriction categories. And then, well, 6 years later, I did my work with Pieter Hofstra on Turing categories. So that's the sort of picture of partiality and, and as you went this way, it became more and more categorical as you went from left to right. Okay, so let's just play around with restriction categories a little bit. The first simple observation is that if F is a monomorphism or a monic map, then F bar is necessarily the identity. Why? Because F bar F is the same as the identity F is F, so necessarily that F bar equals the identity. If you bar a composite, then it's the same thing as barring F followed by G bar. And this is a sort of fairly important observation because it's how you prove that the category of total maps is a subcategory. And here's a little proof of it, the little steps that you do. So the very first step actually is R4 underneath the restriction. And then you can pull out FG bar out of that restriction. And then you can change the order and then put F bar back in and you get what you want. Right. So other useful observations is if you bar twice, well, it's the same as barring once. And probably the most important thing is that they are idempotent. And you can very quickly see that because if you start with F bar, you can push the F bar underneath the bar. And then you get F bar F, all barred, and the F bar F, of course, equals F. So you get just F bar. And then there's a partial order which you can define on the maps by F is less than or equal to F, F is less than or equal to G if F bar G actually equals F. So when you restrict G to where F is defined, then it actually gives you F. And that's a partial order. And in fact, it gives you a partial order enrichment on the setting. So obviously a very canonical example is sets and partial maps, where the restriction is given by, well, F bar X is X if, so it just gives you the partial identity where X is defined. So where it's not defined, it's just not defined. So that's, okay, so as I said, pulling off the total maps is important. What is a total map in a restriction category? Well, it's a map F such that F bar is the identity. And it's important to realize that the total maps form a subcategory. And the proof of it uses that little identity that I proved in a little bit of detail. So if you start with F bar, F G bar, and then you go to F G bar all barred, and then you start knocking off the identity to get what you want. And then there's a theorem, fundamental theorem of restriction categories, that every restriction category embeds fully and faithfully in a partial map category. And so the theory of partiality is completely captured by those four little identities. And I mean, the whole point is that okay, so a partial map category is actually a span, is a span category where one leg, the first leg, is a monic. And if you work at that level, you have to deal with pullbacks and things like that. So it's very much more convenient to work just algebraically. And that was the whole point of the thing. So just very quickly, so how do you prove that fundamental theorem? Well, what you do is you look at the idempotent completion with respect to the restriction idempotence. And then you consider the total maps. Wait, I'm just, sorry. No, I can't do it. the splitting of the idempotents. Right, so you split the idempotents, you look at the total maps inside there, and then you prove that the splitting of the idempotents, the monic part of that, form actually a stable system of monics. So you can actually pull them back against arbitrary maps. And I just shown in this diagram how that works. So the point is that S sub E, I'm going to see if I can just see what happens. Right, hold on. Let me just, yeah. So this map here, S dot E, is a splitting of the idempotent here. And what you want to show is that you can pull that back. And of course, the way you do it is you just use R4 to form the idempotent F, E, all barred. And then you split that. And that turns out to be the pullback. And then you work out, well, that's the partial map category is then actually isomorphic to the splitting of the restriction category. Okay, and then we have to consider products, and it turns out that the products in a restriction category are not quite products, categorical products. They're sort of lax products, because the trouble is when you form the pairing of two partial maps, well, it's only defined to the joint domain of the two components. So just up here, that thing is the same thing as that thing, right? And so, but you do get a universal property that it is unique with respect to that. And then for a final object, well, you get a total map. Oh, sorry, I should have mentioned these projections have to be total, right? And for the final object, you get a unique total map down, such that whenever you have another map to the final object, well, actually, this is H bar composed with this total map. So, okay, so some examples of Cartesian restriction categories. That's restriction categories with the product sets and partial maps, as we discussed, and the product is literally the Cartesian product it sets. But also there's another classic example is topological spaces with partial maps whose domains are open sets. And then another classic example is if you take commutative rings opposite with rational maps. So a rational map in commutative rings is a cospan, where the first leg, what you do is you invert certain elements, and the second leg here is an arbitrary commutative ring homomorphism, and that's, well, is the partial map category opposite, right? And what's sort of interesting is this is the, sort of one of the main subjects of algebraic geometry. So the point is that the restriction categories actually occur all over mathematics, and sometimes in some quite surprising places. So I'm going to talk about another example of a restriction category. Really, I mean, the aim is to build an example which is absolutely central to computer science. So I'm going to start by defining a category called timed sets. So what is a timed set? Well, it's the category sets where the maps actually are going to have timing. So there's going to be, in addition, a map into, well, the natural numbers. It doesn't have to be the natural numbers, but here you are. And that associated with F gives you the timing of F. And F can be a partial map. And the deal is that this timing must be defined whenever F is defined. And then you get identities, which is the thing which has zero timing everywhere. And then you, by composition, you just compose the timings, and then you add the two timings. So the composite of F and G is the timing of F composed with, well, the timing of G, but you have to take it at the image of F, right? And then you just add them. So it's a very simple construct. Now, it turns out, of course, computer scientists don't care about the exact timing of something, and they just consider it up to a complexity order. So what is the complexity order? So it's a class of endomorphisms on the natural numbers, which are monotone. So if x is less than or equal to y, fx is less than or equal to fy, and downward closed. So they're obviously pointwise ordered, right? So if q is less than p and p is in C, you want q to be in C, right? And then there are a couple of other axioms which are convenient to have. The first axiom just says that composites of maps in this complexity class have got to be in there, and the identity's got to be in there. And the last thing is that if you take two of these classes, two of these monotone maps, and you add them, then that's also got to be in the class. A very straightforward thing. So what are examples of the classes? Well, here the angle brackets indicate that you're going to take the downwards closure. So if you just take all the linear time maps, right? So those are maps which just multiply by a natural number object, then that's a complexity order. Obviously, the p-time maps, and it's obviously very classical that people consider this, are also form a complexity class. And then you get these exponential time, much larger complexity classes, where what I have to do is stack up the exponentials like that in order to ensure that you've got compositions and stuff like that. Okay, so, and there are a whole bunch of other complexity classes. I mean, obviously, complexity theory is a big and well-studied thing, but this is enough to get going with. Okay, so now we come back to these timed maps, and what we're going to do is we're going to put a less than or equal to, with respect to the complexity class, to say that F has better C complexity than G. And what does this mean? Well, to start with, F has got to be at least as well defined as G. And then the second thing is that the complexity of F has got to be less than, well, some P composed with the complexity of G, right? So you're not asking that the complexity of F be strictly less than G, but you can sort of bump up that complexity by any member of your complexity class. And that gives you better complexity. And of course, what you're going to say is that F is equal to CG if and only if you get the two inequalities. And, okay, so that equality is actually a congruence on time sets. And I've just written down exactly what that means in terms of how you identify maps. And of course, that means that you can look at T set sub C, and here I've just concentrated on the polynomial timed things. To say they're equal means they have the same polynomial time complexity. So we're reaching into that, the ideas behind complexity theory. So, and it turns out, of course, that this is actually a perfectly good restriction category, where the restriction of a map is given by, well, the restriction of the set map together with the same timing as the original map. And so now what we're going to do is we're going to consider splitting the restriction idempotence. So something magical happens at this stage, because you see, one way to just describe this is the objects, the idempotent on the object now gives a size to each element of your set. And when you have a map between these two size sets, right? So it's a set with an idempotent, but the idempotent then gives you some sort of sizing of each element. When you have a map between them, well, the deal is these are idempotents at either end, and you've got to be able to absorb them into your map. And that means the cost of the map must accommodate both the size of the inputs and the size of the outputs. So intuitively, if you're going to do a map, write a program which takes in a certain input, well, it's going to take you the time of the size of the input, at least, to run that program. And you've got to print out the answer. So it's going to take you the time of the output. So that's sort of intuitively what's happening there. Now, and then you can ask, well, what are the total maps in this category? And it turns out they're exactly the C-timed maps in the usual definition of complexity, where if you're talking about polynomial time, you're given a certain size of input, and then you're allowed to run that thing for a certain polynomial time, and you got to a finish by then. And this is exactly what this formalism gives. Okay, so the point is, once you split time sets P, you get a distributive Cartesian category whose total maps are precisely the polynomial time maps. So there's still an issue of, well, how do you isolate the p-time maps as used in computer science? And of course, this is where the Turing categories come in. So I'm going to flip back to talking about Turing categories. So what is a Turing category? Well, it's a Cartesian restriction category with a Turing structure. So a Turing structure is an object together with, for each pair of objects, a bullet. So the type of the bullet is given down here. Yes, you can see my my funny black mark moving around. And the deal is that given any f from A cross X to Y, there's this code for f, which is a total map from A to T, such that when you compose it with this bullet, and of course the bullet, this could be partial, and so the bullet will definitely be partial. When you compose it with that thing, you get back f. So in other words, the source, you can think of it like a little program that you're putting into the Turing object, and that when you run that program on with input X, you get out Y. And that's the definition of the Turing category. So one thing to observe is that in a Turing category, every object is actually a retract of the Turing object. And here's a little proof of it. Well, so for any A, actually, I've flipped the order of the, did I flip the order of the? I did, I'm sorry. Oh, no, I didn't. No, I'm fine. Okay, sorry. All right. Yeah, so for any A, this thing is the identity map, essentially, except you product it up by the final object. And you're just going to take projection, which is a total map. And that tells you there is a code for that thing, for the bullet subscript 1A, right? And that tells you, in fact, that A must be a retract of T. So every object in a Turing category is actually a retract of the Turing object. And that means you can re-axiommatize it. So a Turing category has a Turing object, and every object must be a retract of that Turing object. And actually, you can get away with just one application, which would be bullet T. And so it's going to be look like this. And this is what's commonly called the Turing map, because you just have a Turing object and a Turing map, and then that's enough to actually define things. And there's one other observation I should, so the question is, how do you get these other Turing maps for powers of T? Well, what you start doing is just stack the application like this, and that gives you the Turing map that you want. So this is, right, here's the Turing object. Here's the object for which you want the Turing map. And you go to T. Okay, so the sort of key observation is to connect this up to partial combinatory algebras. And the point is that in a Turing category, the Turing object is necessarily a PCA. And just to remind you what a PCA is, a partial combinatory algebra is. I'm going to describe it set in a Cartesian restriction category, so you can define it best in there. So it's a partial map called application from X cross X to X. And then there are combinators, which are maps from 1 to X, and these got to be total. And then you just have 3 identities. Sorry, 2 identities. So KXY has got to equal X, and SXYZ has got to be XZ applied to YZ. And then there's a requirement of that S applied to X applied to Y is total, and KX is total, right? And that's it. And it's sort of well known that from such a simple system, you can get all computable maps. So it's sort of nice to be able to connect this up. Of course, we're talking about a Turing object now, not in sets, but actually in a Cartesian restriction category. And so that's important. And you can go backwards, you see. If you have a Cartesian restriction category and you have a partial combinatory algebra, then what you can do is you can look at the so-called computable maps of that partial combinatory algebra. And the point is those computable maps actually then give you a Turing category. So the point is that from a Cartesian restriction category, you can isolate a Turing category if you have a PCA. And this is, I mean, a fundamental sort of construction of things. Let's just discuss when is a map F. So obviously the object's going to be generated by this object X of the PCA, and you're going to take all products of that object, including the final object, of course. And then you're going to look at the so-called computable maps. And the computable maps are the ones which have codes. So, and you take the stacking of the application over here. And so F is going to be computable if there's a code which gives this map. And the magic of combinatory algebras says that the maps which are given by codes can actually be composed. And so I'm not going to go through that, but it is something which is very fundamental to combinatory algebras. Okay, so that gives you a way of extracting from a Cartesian restriction category a Turing category. Okay, so the question is, can we identify a PCA in the split timed split t-set P, right? Which are the polynomial time maps in things. And the answer is yes, right? So we're dealing with the p-time complexity class here. And in fact, if you look in any classical complexity theory book, what it does is it shows, I mean, it uses the model of a Turing machine, and it shows that the steps of a Turing machine actually can all be done in p time. And so that means you can define a Turing machine inside the category of p time maps, which is sort of fun. But then a Turing machine actually automatically gives you a PCA. So that's, I'm not going through the details of this at all, but the point to stick in your mind, and it's important, is that what complexity theorists have done is they've isolated a timed PCA, a polynomially timed PCA, in this strange split t-set P category, and they start working with that. So, so why did I find this interesting? Well, because it unifies computability and complexity. Both are, you know, the theory of a Turing category, right? Comes from the theory of a Turing category. And the other thing is, I mean, it gives you a very explicit model of what complexity theory, what categories complexity theorists are actually working in, which I think is sort of important to have that model around. Now, and you'll notice, of course, that because in the original, in split t-set P, the total maps are exactly the polynomially timed maps, that you're not going to get any more total maps when you start taking out the computable maps for a Turing object or for a PCA, right? So that guarantees that the maps, the total maps, are just the p-time maps. So this is sort of also an interesting philosophical observation, because you would have thought that because a PCA always gives you all computable maps, that it should have more than the p-time maps as total maps. It should have all the other computable maps. But that's not correct. In fact, if you set things up right, you just get the p-time maps out as the total maps. Okay, so it's sort of also interesting that one of the difficulties we had was we asked, well, how far can you push this down in the hierarchy of complexity orders, right? In particular, can you have a Turing category which has exactly linear time maps, right? And it turns out the answer is yes. And this was a bit of a surprise to us. We couldn't actually do this directly from the construction that I got, but Pieter helped determine exactly which category is going to be the total maps of the Turing category. And it turns out that linear time maps actually sort of fit that criterion. So, I mean, the point is, Turing categories in complexity terms go right the way down there. And I've always found that quite a shock that does happen. Okay, so I'm actually, I don't know, how is my timing going?
You're doing great. I mean, if you want to wrap up in like 10 or so minutes, we also started about 5 minutes late, so you know you could. It's like
well, I've done myself here. Okay, so things left undone. So really, this is my concluding slide. I mean, one of the obvious things to ask is, well, okay, so is there an initial Turing category? And the answer is yes, there is. And how much do we know about it? And the answer is, well, unfortunately, not very much. Right, indeed, there should be a rewriting theory for this. Now, the rewriting theory has this extra sort of difficulty. You've got to handle the partiality. And that turns out to be pretty tricky. We never really sorted that out, although this was something that Pieter and I started looking at seriously to try and understand that the granddaddy of all computability notions. And then you can start asking questions about, well, what happens if you have a reflexive Turing object? So by that I mean that the set of partial maps actually is a sub-object of the Turing object. So that there's an idempotent which if you split gives you the partial maps, and you can start asking, well, okay, so what is the rewriting theory in that case? So that gets you into the partial lambda calculus, and actually trying to get a rewriting theory for that. And still that, we still don't know how to do that, right? I mean, Moggi looked at this in his thesis, but I have to say it was a bit of a mess. And we really need, it would be useful to have a very clean version of these fundamental things. And then you can start looking at computability of special Turing categories. So the question is, well, how much of computability theory can you get out in Turing categories? And in fact, in my Estonia notes, I end off by actually doing some of this. And you can get quite a long, I mean, you can get through what I would describe as the first course in computability theory, and you get most of the results in there quite easily out of a general Turing category. Actually, you had to have, I mean, significantly, you've got to have joins in this, in such a thing to get things going. And then there's another sort of big issue. I mean, so it's obvious. Okay, we got Turing categories which have partiality, but you can have Turing categories where all maps are total. And so the model of just the untyped lambda calculus, which not the partial version but the total version, right? That gives you a Turing category where everything is total. So the point is, you can look at having a Turing object in different settings. So, for instance, you can look for a Turing object inside a symmetric monoidal category or a multi-category. You can look for Turing objects inside differential categories. And of course, that literally gives you a model of the differential lambda calculus, right? And you can look for these models inside polycategories, linearly distributed categories. So there's a whole sort of industry that you can start up there. And we really don't know actually very much about these things. There isn't, a clean geography that you can go to tell you about all these special cases of Turing categories. Okay, well, I am going to wrap up now. So that's the end of my talk. Thank you for listening. And if you have any questions, I will.
Yep. Thanks, Robin. That's great. Yeah, so I have questions, but first I'm going to see if other people so if you have a question, you can raise your hand on Zoom, and we should be able to see it. Oh, Valeria, go ahead.
Oh,
Valeria, did you want to ask a question? Okay. Okay, I will ask then. So you had an interesting sort of comparison of the different approaches to like notions of partiality at the beginning. And one thing that I'm aware of is so there's this work by Carboni and Walters on bicategories of relations. And as a sort of side note to that, I think Carboni wrote a paper on bicategories of partial maps, where there's sort of a two-categorical or bicategorical approach to describing how total functions are embedded in partial ones. And so I was wondering if you could explain what connections exist between restriction categories and these the more this bicategorical approach.
right. Well, they're the same thing, right? But
okay, they're actually the same.
Yeah. I mean, what Carboni and Walters did is they simplified. I mean, they wanted to have a general bicategorical approach, and then they found the coherences were a bit much, so they just simplified to the case where they had a partial map. Not partial map. Well, they had a poset enriched setting, and that works out to be the same as a restriction category.
Interesting. Okay.
So, yeah.
Thanks.
So that's a different approach. But obviously that then, goes off into the non-posetal side as to what's happening. So.
Right. Thanks.
Oh, hi. Whoops.
Evan, are you seeing everyone? Can I have my question now?
Yeah. I tried to call on you, but maybe you couldn't hear at the time. Yeah. So please go ahead.
So many thanks, Robin. Very interesting. I have a question about one of the things that you're saying at the end. I want to know which of the terms of traditional recursion theory you actually proved, and under which restrictions on the restriction category. So if there are any restrictions, right? If it's not any restriction category.
Okay.
Things like the SMN theorem and kind of
I think
stuff like that.
Yeah, the SNM theorem is almost immediate. So but I mean, things like Rice's theorem, right, are sort of more interesting, and the fact that the halting problem is a generic subobject. In other words, every computable subobject can be got from it, right? So those sorts of things were easy to get out, and various other things. So yeah.
Reduction orders and stuff like that.
Reduction orders.
Yeah.
Yes. Good question. I mean, it's all in there, I guess. Yeah. I mean, yes. I mean, the trouble there is to, the actual reduction orders you get are very specific to the particular model, right? Yeah, and I think that, yeah, that needs to be studied more.
Yeah, that also sends you to the more kind of logical side of that, right? Kind of getting things like triposes and effective topos and stuff like that.
Yeah, so just a comment about that. I mean, one of the, right, once you're in a topos, of course, you have an awful lot of logic. The thing that I like about a Turing category is you have virtually no logic. So you get the bare computability there. And in fact, I mean, from just a categorical perspective, these time sets models and the p-time models, they're really good for counterexamples. So it's often hard to think of a counterexample. You know, we tend to, as a category theorist, we tend to think in terms of infinite limits and stuff like that. Mm-hmm. And of course, you know, these complexity models don't have infinite limits. So you really are, you know, restricted. And that means that when you want an example of something which normally you would prove very simply using an infinite limit, usually it doesn't happen in a p-time category.
Right. Well, thank you. That's very interesting. As is the business of having all the polytype, not having more computable functions than the polytime ones, if I understood you correctly. Do you mind repeating that kind of quickly?
I'm sorry, I missed that last bit.
I was asking if, you know, I think you said that we get that all computable functions are polytime. You did. Okay. I was just asking to repeat that because I was not so sure that I understood correctly. But yeah, that's very interesting too. Thank you.
Yeah. Thank you for the questions.
Evan, there's a question in the chat.
Oh, is there? Okay.
Oh, there's a question in the chat. I should look at
kind of. It's just saying
computers I got going here.
Why is the Turing church thesis crossed on the last slide? It's a good question.
Okay. Right. Why did I do that? Well, right. The church Turing thesis says there's only one notion of computability, right? And and really what this is saying is, no, there are lots and lots of different notions of computability. And, you know, and some of these notions were, you know, I mean, the minute you went into complexity theory, well, you got a different notion of computability. So, so if you take the church Turing thesis to mean that, and that's often how undergraduates, certainly going through computability theory, will take it as meaning whatever you do, you always get the same class of functions, right? But in fact, that, I mean, in generality, at that level is not true. But of course, I mean, there are finer interpretations of the church Turing thesis, which are still valid, but you have to say precisely what it means. Right? So that's why I crossed it out. I hope that answers that.
The person who asked the question is saying, okay, thank you very much.
Okay.
Okay, well, thanks. So let's thank the speaker again. That's great. I am going to stop the recording.